All right. I think there is a homework assignment due today, right? Did you have any questions about that homework assignments? I think I saw many of you already turned in homework 5. Okay.
I have a question about the exam real quick.
Okay, go ahead.
So I wasn't able to submit 2 pictures.
Oh yeah, so I actually created like multiple questions, like repeat the same question. I think I had like 10 of them. So if you have multiple pictures, so for the last 10 questions, you don't have to there, you just submit your pictures. So one for each, one for each.
Okay.
Yeah, so you can submit at up to 10 pictures. I think 10 pictures should be enough. Okay. Any other questions? Okay. So the worst case, if for some reason, I don't know, anything could happen with, with the computer technology. So what the worst case, if you were not able to attach your documents, the worst case, you can email all of them to me. Okay. But again, if you email to me, I kind of have to remember that to go back to my email to find it. But if you attach it, I'll just go to Blackboard and to find your pictures. Okay. So
I have a question real quick.
Yes. Yeah, go ahead.
Is it timed?
Yes, you will have 1 hour, 30 minutes to take the exam and 15 minutes to take pictures and attach pictures and to do all that. So you should have the first exam, you should have enough time to, I think 2 students took it and I think they both finished before 90 minutes. All right, other questions? All right, okay, so just remember to take it before Sunday midnight. All right, now today we're going to move on to section 3.6 and 3.7. All right, let me share the PowerPoint slides with you. All right, so chapter 3, we started to learn how to write proofs. We learned different methods of proof. In 3.1, let me just review the methods we learned. So first we learned direct proof, and then we learned proof by cases. I think we talked about was it last Thursday, proof by cases, which is also the homework that you will turn in today. So here. So overview of chapter 3, section 3.1, 3.2, 3.3, they are all direct proofs. So we learn how to prove expression, mostly a number or algebraic expression is either odd or even. And we also learn how to prove expression is a rational number, rational expression, I guess fraction. And we learn how to prove a number divides another number. And in some cases, so usually when you get a proof question, you first want to try direct proof, see if you are able to do it. Well, if you can't, then you will have to try other methods. For example, proof by cases. And as you saw before in your homework assignments, like homework 5 or the examples we saw before, some of the expressions you will not be able to factor out a let's see, let me write it down, a quick example here. So for example, if I give you n squared plus n, I can tell you this is always even. But if you try to prove directly, you can't, because in order to prove a number is even, you have to be able to factor out a 2 times something. But apparently n squared plus n, by looking at this, we cannot factor out a 2. Well, however, if you do by cases, case 1, n is 2k. Case 2, n is 2k plus 1. It's by 2 cases. So we prove it case by case. So the first case, if n is even, I plug this back into the expression, I will be able to factor out the 2. If n is odd, I should still be able to factor out the 2 after I replace n with 2k plus 1. And you can prove this expression is even for both cases. Of course, if one of the cases fails, then you cannot say it's even. But both cases, under both cases, after we plug the expression in there, we can prove, we can always factor out a 2. All right, so that's when do we have to use proof by cases? When you try to do one case, it doesn't work, and you do by cases. And also, I talked about this before, although we didn't have any questions. You could also do 3 cases, 4 cases, or even 5 cases. I mentioned it before. When we publish a research paper, oftentimes we have many cases, like 10 cases or even 20 cases. It's possible. But how many cases do you divide into? It depends on the question. Okay, so if I want you to prove an expression is a multiple of 3, you want to factor out a 3 instead of 2, but this one probably doesn't work. But any expression, if they want you to factor out a 3, you might need to do 3 cases. I don't know if you still remember that. You can do 3k, 3k plus 1, and 3k plus 2, which represents 3 categories of integers. 3k means this number is a multiple of 3, and case 2 means it's a multiple of 3 plus 1, so with 1 left over when you divide a number by 3, and or 3k plus 2. When you divide a number by 3, you have a leftover 2, so remainder 2. So you could do 3 cases. And how do I know I should do 3 cases? You could try 2 cases. You will find out, oh, it doesn't work. Maybe I should try 3 cases. The other hint is you want to factor out a 3. Probably you need to have a 3 in the expression, so you will be able to factor out a 3. If you have 2 in there, you may be able to factor out a 2, but you may probably not going to be able to factor out a 3. Okay, so how many cases do we have to do depends on the problem. All right, so that's the second type of proof method we learned. So today, I'm going to talk about the last one. Well, not the last one, the third one for this chapter. And there, in chapter 4, we are going to learn another proof method next week called mathematical induction. But for chapter 3, this is the last one, indirect proof, or you can call it proof by contradiction. So in section 1.3, when I talked about arguments, I gave you this example. So we can take a look, go over this again. So if you remember, this is one of the slides we had in under section 1.3. So what it says is, suppose you want to prove, Mike wants to prove he did not make those long distance phone calls, which ended up with a huge telephone bill. So he wanted to prove that to his dad, that he did not make the phone calls. So usually in real life, you would say something very simple like, if I, excuse me, so when he said, oh, I was in school, how could I make the phone calls? Well, so this is pretty much indirect proof. When we write it down formally, so first thing you want to say, suppose I made the phone calls. This is what we call a negation, if you remember. So he wanted to prove he did not make the phone calls. If I call that statement P, I made the phone calls, that's the negation of did not make phone calls, so the not P. So the first step, this will be your first step. You always want to say the opposite. Suppose you make assumption that opposite is true. Although you want to prove P is true, but you want to assume the opposite is true. So suppose I made the phone calls. then you should be able to draw a conclusion. Something will follow from that assumption. So if I made the phone calls, then I had to be home. Let's say if the telephone bill tells you a long distance phone call was made at 1 p.m. on Thursday. So that means if he made the phone call, then he had to be home at 1 p.m. on Thursday. But that's the fact. The fact is he was at a school. Maybe he was he had teachers or classmates who could prove that he was at school. So this is a fact. So you now look at these two sentences. The first sentence, I had to be home at 1 p.m. on Thursday. That comes from the assumption. Actually it was a false assumption, but we assume it is true temporarily. So if I made the phone call, I had to be home. So this is the conclusion drawing from the assumption. I was at school at 1 p.m. on Thursday. That is a fact. And these two statements, they are contrary to each other, because as a person, you cannot be at two different places at the exact same time. So you cannot be home and at school. So that tells us there's a contradiction. Well, that contradiction tells us, because that second sentence, I was at school at 1 p.m., that's a fact. You got proofs, you got alibis, and so that's a fact, which means this has to be true. Well, when you have two statements, they're contrary to each other. If the one of them is true, that tells us the other has to be false. Okay, so that means I cannot be at home. How did I get I was home? Because I assumed I made a phone call. So if this is false, it just tells us I couldn't make the phone call. Okay, so this is sort of like the contrapositive. We talked about it before. Let me write it down. So let's see. What we said is this conclusion. So if I made the phone call, implies that I was home at 1 p.m. But now we know I was not home at 1 p.m. Now what conclusion can we get? Can you draw the conclusion? So let's call this maybe statement A implies statement B. If I made the phone call, then I had to be home at 1 p.m. That is true. But now I know I was not home, which means that's a negation of B. If I was not home, what conclusion can follow from this?
You didn't make the phone call.
Yes, very good. You did not make the phone call. That is the contrapositive statement we talked about it before. And we also said many times the contrapositive and the original implication, they are equivalent. So this symbol here means equivalent, which means they are, they're technically the same thing. It's just different ways of saying the same thing. So if I was not logically equivalent, so I was not at home, and then I did not make the phone call. I didn't make the phone call. So that kind of proves your point. I did not make the phone call. Okay, so how did we know I was not home? Because there was a contradiction. If I was home, then that would be contrary to a fact that I was at a school. So this is a fact. This statement right here, which is true, that's a fact. But that statement, it just comes from your assumption. So if the fact has to be true, which means your conclusion, I had to be home, has to be false. Okay, so if I was not home, that tells me I did not make the phone call. So he proved his point. He did not make the phone call. All right, so in real life, we do use this kind of argument a lot, but you may not realize it's called indirect proof, or proof by contradiction, or proof by contrapositive. So here we're going to summarize the steps that we just saw here. Look, the first step, we always assume that negation is true. So the first thing you want to do, assume the negation is true. Take the negation of the statement. Let me write, I have steps here. So the first step, suppose the negation of the conclusion is true. He did not make the phone call, but we assume he made the phone call. And step two, you want to find a a contradiction of whatever the conclusion you draw from there with the fact. So in mathematics, usually the fact could be a theorem, could be some definition, could be just something like a common sense. And so you will find where the conclusion you draw from that assumption is contrary to some kind of theorem or definition, which means the conclusion has to be false. Goes back to your assumption has to be false. If your assumption is false, the negation has to be true. So that's the process. The final step, you would just have to conclude the negation is false, which means the conclusion is true. All right. So like in this case, so we concluded that negation is false, which is the assumption. So I did not make the phone call, which means, well, this is false. Okay, so I made the phone call is false, which means did not make the phone call. Okay, now here I have another example, real life example. Suppose a man was killed at the park. The forensic evidence showed the man was killed between 11 to 12 p.m. in the park last Thursday. Okay, so if someone accuses you, here I just give a name, just call, say Cody, of killing a man. So you want to prove Cody did not kill the man. Suppose, say your name is Cody. So well, or if you are the attorney to defend for Cody, and one of the approach you can use is indirect proof. So step one, suppose the negation is true. So you want to prove Cody did not kill the man. You would take the negation of that. Cody did kill the man. Suppose Cody killed the man. And next step is you want to find a contradiction. So step two, if Cody killed the man, then Cody, well, should be Cody here. So Cody had to be at the crime scene, which is the park, but from 11 to 12 p.m. But Cody actually was in a class. And so we could be the alibi. And so the contradiction is, again, the same, very similar. So a person cannot be at the two different places at the same time, during the same time. So that's the contradiction. And after you found the contradiction, so step two is the important step. How do you find a contradiction? So a lot of questions in math theorems, it's not going to be very straightforward like this. Where the contradiction is because Cody cannot be, let me write down, Cody can't be at two different places during the same period of time, two different places during the same time. So that is the contradiction. Okay, but when we have, I'm going to show you examples after this, math examples, you will see sometimes it's not very easy to see what to find a contradiction. So once you found a contradiction and you can stop and just conclude that, all right, so where does the contradiction come from? The contradiction comes from your assumption, because your assumption is false. That's how you get a contradiction. If your assumption is false, its negation has to be true. So you conclude negation is false, the original conclusion is true. Okay. All right. So these, whenever you use indirect proof or proof by contradiction, there are three steps here. So now we can look at first example. Prove there is no greatest integer. I think everyone knows that, you can always come up with a number when you can keep adding. Well, that's the idea of the proof. So if you say, 100 is the greatest, you have 101 or 102 and so on. If you say 1 million is the greatest, there's a 1,000,001. And then if you say 1 trillion is the greatest, then maybe you can always add a 1 to it. So actually that's the idea of the proof. If I don't know if you notice that when I say it, suppose you say 1 million is the largest. Well, in fact, we want to prove there is no largest integer. But instead, you say, okay, if there is one, say 1 million or 1 trillion, then I can add 1 to it, which is bigger than 1 million. If I add 1 to 1 million, 1,000,001 is bigger than 1 million, which proves that 1 million is not the largest. But if you say 1 million and 1 is the largest, I can keep adding another one, 1 million and 2, right? 1 million and 3. So this proves there's no greatest integer. So we're going to follow the steps to write down the formal proof here. So first step, you always negate this. Take the negation. Write down the negation. We learned how to do that in chapter 1. So prove there is no greatest, right? So I'm going to assume, suppose. You can add, say, suppose to the contrary, but you don't have to say that. There are different ways to say. You can say, by way of a contradiction, we assume that there is. I'm going to show you some different ways you can write. So there is a greatest integer. All right. Okay, so remember how to write down negation. No greatest integer, the negation will be there is a greatest integer. So you can say, just say suppose that, or you can add suppose to the contrary, that there is a greatest integer, or you can even say by way of contradiction, we assume that there is a greatest integer. Okay. All right, so now we've done the first step. Now, second step, which is the most important step, to find a contradiction. All right, so if there is a greatest integer, what's going to happen? Okay, let's assume, well, we can go ahead and call this greatest integer n. Okay, let's just call it n, say n. Okay, let me make it a little better. Okay, there's a greatest integer, say n. Let's call this greatest integer n. I mean, in real life, you may say, okay, 1 million is the greatest. If somebody tells you 1 million is the greatest, you can add 1 to it. If somebody says 1 trillion is the greatest, you can add 1 to it. So here, we don't have to use a specific number because we can use a variable and to describe it without specifying which one is the greatest. But if somebody tells you there is a greatest, because different people may have different ideas. So maybe one person say 1 million is the biggest. Maybe somebody else says 1 trillion is the biggest. But it doesn't matter what that is. If there is one, we're going to call it n. N represents that largest integer. So now we're going to find a contradiction. So then we can create a number. Maybe I can just, in this case, we can get the contradiction immediately. So let me just go ahead and write down the contradiction. Since n plus 1 is greater than n. So there's this is contrary to the assumption, our supposition or assumption that n is the largest. Or greatest. Let me just use greatest integer. All right. So here we can find the contradiction immediately. What's the contradiction? If n is the greatest, you shouldn't have any number, any integer that is bigger than n. But we did find another one, which is n plus 1. That's definitely bigger. Whenever you add 1 to an integer, it's going to be bigger. And is the contradiction. Now, after we found the contradiction, you can conclude. So the assumption is false, which means original is true. So maybe you can just skip that, saying the assumption is false. You can just conclude that. So there is no greatest integer. Okay. This is a simple example because how you found the contradiction is, I think it's straightforward, just like in real life. If there is a greatest one, and you can add 1 to it to make the new number, you created a even bigger integer, which is already a contradiction. Because if n is the greatest, you shouldn't have another bigger one, but we did find a bigger one, which is a contradiction. Okay, so any question about this example? Okay, so if not, let's look at the next example. So prove that if n squared is even, then n is even, where n is an integer. We did something similar to this before, and we use a direct proof. But in that case, that example is very different. I'm going to write down a similar question we did before was prove that if n is even, then n squared is even. So you can see that's the hypothesis and conclusions switched. So in this case, we know n is even, and we want to prove n is even. We know the square is even. We want to prove the base is even. But previously in section 3.1, we proved something like if we know n is even, the base is even, then when you square it, it's still going to be even. As you can see, they are really they're converse of each other. And we know before, so we proved this before. This is proved previously. And you just assume n is 2k, and then n squared will be 2k squared. After you work this out, you get 4k squared. Apparently, you can factor 2 out of 4k squared. So we proved immediately n squared is even. So this is proved before, and we used direct proof. Okay, but now if I was try to prove the converse is also true. From chapter 1, we know converse may not always be true. Sometimes it's true, but not always. In this case, the converse is also true. But how do we prove it? So if you try to use that direct proof, the same method we did before, it's not going to work. Why? Because this is given. If you know n is even, you can assume n equals 2k, and you just square 2k. You can get an algebraic expression, which is also polynomial. You can factor out a 2. But if they tell you n squared is even, let's say, can I assume n squared is 2k? Well, yes, you can. But unfortunately, how do you get n from n squared? Well, in 3.1, because you want to go from, you are given n, you want to get n squared, you square 2k. If n is 2k, you square 2k. But if n squared is 2k, and how do you get n? How do you solve for n?
You take the square root.
Yes, very good. Thank you. So you take square root. Well, here's the problem. How do you factor 2 out of square root? And that's why it doesn't work anymore, direct proof. Okay. And so as you can see, why do we have different methods, proof methods? For example, why do you have to do cases like the one I showed you before? Why do you have to do case? Because there's no way you can factor 2 out from there by looking at n squared plus 1 plus n. Same reason here. If you try to use direct proof, because this is given, okay, they tell us n squared is even, and they want you to prove n is even. You don't know whether n is even in this case, okay? So we only know n squared is even, so I can assume n squared is 2k, but in order to get n by algebra, you will have to take square root. Well, when you look at the square root 2k, you don't know what k is, so there's no way you can factor out a 2 from square root, okay? So that's why it doesn't work this way anymore. Okay, so be very careful. In the past, I did sometimes see students who did exactly the same way, like 3.1. So when they did the questions, again, this way I should say does not work. So it's still correct. Assume n squared is 2k, take square root. But when we get here, we get stuck. We cannot continue to factor out the 2. How do you factor out 2 from square root? It doesn't work. But there's a wrong solution, which is this way. The idea is good. It just doesn't work. There's a wrong solution, which is completely wrong. In the past, I saw students do this. They did exactly the same thing as the problem we did in 3.1. Well, this will be completely wrong. Why is this wrong? You cannot assume n is 2k, because the question is asking you to prove n is even. So if it's just like if I ask you to prove Cody is innocent, you cannot start with the sentence say, since Cody is innocent, he shouldn't be sentenced, right? So the judge will be asking why Cody is innocent, because that's what you supposed to prove. You're supposed to prove Cody is innocent. And you cannot start your argument with, since Cody is innocent, because Cody is innocent, it doesn't make sense. So the same reason, if somebody asks you to prove n is even, this is something we need to prove. So prove n is even. You cannot start with, oh, since n equals 2k. Well, it's like saying you already know n is even. If you already know n is even, there's nothing to prove, right? And so that's why this is completely wrong, okay? So you cannot assume n is 2k. Previously, we were able to because they told us if n is even, prove n squared is even. So previously, we were supposed to prove the square is even, and we know n is even. But in this case, they want us to prove n is even, which means we don't know. Before you prove it, you don't know whether n is even or not, okay? And so the same reason, just like if you think about the real life example, if you want to prove Cody is innocent, you don't know whether Cody is innocent. You have to list all the evidence to show why Cody is innocent. You cannot start the argument with the since because Cody is innocent. So that doesn't work. Okay. All right. So just pay attention to those things. So here, all this explanation, it's not the proof yet. It's just my thinking. I'm trying to explain to you why we have to do proof by contradiction. Why do we have to use indirect proof? Because all the proof methods we had before don't work anymore. Even if you do cases, it's not going to change anything. Plus, we don't really, I guess, we know n squared is even. I mean, there's not really two cases to do. You already know n squared is even. You don't need to assume n squared is odd because n squared, we already know it's even. So you don't do cases here either. Okay, so here we're gonna try indirect proof, see if it works. So all this, you don't have to write in the proof. This is just my explanation to you why we couldn't do the direct proof or proof by cases. So now here's the correct proof. So first step is still we assume. Suppose, what do we assume? Follow the steps. You assume the negation is true. So in this case, what would be the negation?
N is 1.
Any is what? Say it again.
That N is odd.
Did you say 1?
Odd.
Odd. Okay, sorry.
Sorry.
Yes, that's right. Very good. Okay. Suppose that n is odd. Very good. Okay. So we assume this is the negation. And they want you to prove n is even. You take the negation, which n is odd. So you assume n is odd. Okay, what comes from that? If you know n is odd, you can. So we're done with the first step. Now we're just trying to do second step, contradiction. A lot of times you probably, excuse me, you probably don't know where to find a contradiction. So just use what you know. For example, okay, n is odd. Usually when somebody tells you n is odd, what can you assume immediately? How do you describe an odd integer?
That it's 2 plus any, or 2 times any integer plus 1.
Yes, that's right. Very good. So if you say, well, I don't know how to find a contradiction, well, just look at your assumptions, see if you can get anything out of that. That's exactly right. Is that a Marley? Was Madison? Okay. All right. So yes, that's right. Madison is right. So you can assume. So since you know n is odd, that's your assumption, and then you can n equals. You can let n be 2k plus 1. You can use the letter k. Okay. All right. So we got this. So far, we don't have any contradiction yet. But look at the hypothesis given. So this is given. Whatever the hypothesis, it's something given. So you can use that. So it says n squared is even. See, look, we have an expression for n. It's easy to do n squared. So let's see what happens to n squared, because the hypothesis says n squared has to be even, right? But now, since we know n is 2k plus 1, so I'm going to try to find out n squared, what n squared is. And that part is algebra. You got to do FOIL. Well, if you memorize the formula, you can use the formula, but be careful. You cannot take 2k squared plus 1 squared. You got to do FOIL. So that should give you 4k squared. 2k times 2k, that's 4k squared. 2k times 1, it's 2k. And 1 times 2k is also 2k. And 1 times 1, that's also 1. After you combine like terms, you should get 4k squared plus 4k plus 1. And now take a look at this expression. What kind of number do you think this is? Even or odd?
Odd.
It's odd, right? Can you all tell it's odd? And you can do what we did before, factor out a 2 from 4k squared and to 4k. So let's do that. And there's leave a plus 1 there. Because notice this is a multiple of 2. 2 times something, that's a multiple of 2. It has to be even. Even plus 1 is odd. Okay, so here, can you see what the contradiction is now? Can you all see what a contradiction is now? See, what did we just prove? N squared is what? It's odd, right? Do you see that? So we went through all this algebraic work and we found out n squared is odd. Now, this is contrary to what? What is this part contrary to?
The given statement.
Yes, that's right, Tyler. Okay, what's the given statement? The given statement or the hypothesis, this is given, n squared is even. So the problem tells us specifically n squared is an even number, an even integer. But we found out we can prove n squared is odd. So that's a contradiction because n squared has to be either even or odd. It cannot be both even and odd. We know we don't have integers that are both even and odd. So one of the things has to be false. So let me write down here clearly. So this is given by the problem. What's given? N squared is even. But what we just proved is n squared is odd. We proved, I guess I just put it, we proved n squared is odd. So which means, well, what's given has to be true. You know, you cannot, this is what they tell you as a fact, as a given condition. This is the condition. So this must be true. If this is true, it only tells you, well, what we just proved is false. But if you say, how can we prove something that's false? Well, there is a reason because how did we get this conclusion n squared is odd? We had a false assumption. That just tells you this conclusion comes from what? This comes from our assumption n is odd. So what we just proved is based on this condition. Based on which condition? N is odd. If n squared is odd, it's false, which means whatever we are based on is false. So n is odd has to be false, which means the negation has to be true. Again, that's something we discussed in chapter 1. When you have two statements, they're negation of each other. If the original is true, then negation is false. If the negation is false, of course, the original is true. So that just tells us whenever you get here, you can pretty much stop. You can say contrary to, so you can add a sentence, say contrary to, if you be more specific. It's pretty obvious here, so sometimes we may just say a contradiction. But for the beginners, probably you should write down contrary to the condition, the hypothesis, or you can say the hypothesis, which says that n squared is even. Just add one more sentence after this. And usually, again, like if you read a research paper, usually when they get a contradiction, they automatically stop because everybody knows. And when you reach a certain level, usually whoever can read the research papers, usually they already learned and they understand how proof by contradiction works. So usually you can just stop right there and automatically tells you n cannot be odd, n has to be even. But for us, for the beginners, probably you should write down one more sentence after this. Therefore, n is even. Okay, how did I get that? Because if n is odd, you're going to get a contradiction, which tells you n cannot be odd. If n cannot be odd, then n must be even. So that's how you prove that statement. Okay. All right. And so, so previously in 3.1, we proved if the base n is even, then when you square it, you still get an even number. But in this example, we proved if the square is even, the base must be even. Okay, the base n must be even. It cannot be odd. All right, so that's how we use indirect proof. Any question about this example? Okay, so when you write down the proof, this is where you start. But usually, when you get a question, you may say, how do I know I should use indirect proof? You would try direct proof first. See, this is what my try. I try to use direct proof. What's direct proof? Which means whatever they give you, you use what they give you. This is what they give us. N squared is even, so I'm going to assume n squared is 2k and try to see if I can prove n is even. Try to factor out a 2 from here. I found out I couldn't, so which means my trial failed. So that tells me I have to use indirect proof, or I could use proof by cases. But again, proof by cases doesn't work here either because we, n squared is even, so it's just pretty much one case, n squared is even. Okay, so that's the second example. Let's see if we gonna do more examples here. Okay, so I'm gonna do maybe another example about rational number and okay. So example 3. So we want to prove. So the question says use proof by contradiction, which is also called indirect proof. Use proof by contradiction to show that the sum of any rational number and any irrational number is irrational. All right. Now, previously in 3.2, I asked you to do. I gave you examples and asked you to do homework problems. Usually, the questions are like previously in 3.2. We gave you a rational number, which means a fraction. A rational number plus rational is still rational, or the rational number minus rational is still rational, or a rational number times a rational number is still rational. When a rational number divided by rational, make sure, I guess it's non-zero. Rational number is still rational. So these are the statements we proved before. What we did is direct proof. So if they give us two rational numbers, I just start with a over b plus c over d, or a over b minus c over d, or times. And well, you simplify that, and you should be able to get something like an integer on the top over integer on the bottom. But in this case, we want to show the sum with still addition of a rational number. Well, any rational number can be described as a fraction, a over b, and what? Irrational number. There is no expression for irrational number. Irrational number we know, such as pi or square root of 2, or square root of 7. Those numbers are irrational numbers. Irrational number just means you cannot describe it as a fraction. So which means, for example, pi, you cannot describe as like integer divided by integer. You cannot find such fraction. Okay. Similarly, for square root of 2, you can't find such fraction. So for irrational number, we cannot really describe it in a certain format. Previously, like we say, if you know something's even, you can write it as 2k. If you know something's odd, you can write it as 2k plus 1. If you know you have a rational number, you can describe it as a fraction. But irrational number, you don't have any description. Well, you can just use one single letter. maybe I can just use X to describe this. You can use any letter. Okay, so we want to prove after we add a rational number A over B and an irrational number, let's call it X, and we want to prove after you add them, you should get irrational. It must be irrational, which means it's not going to be a fraction. Okay, so in this question, we are supposed to prove something is irrational. In 3.2, I never ask you to prove anything is irrational. I always ask you to prove something is rational because you can prove it directly. How do you prove something is rational? All you have to do is to show it is some integer divided by integer. That's it. So if you can describe it as integer divided by integer. But how do you show something is irrational? Which means you have to show this number, whatever, is not a fraction. I mean, how do you, for example, if I give you square root 2, how do you show square root 2 is not a fraction? I mean, it's easy to show something is a fraction, but you cannot, it's very difficult to show something is not a fraction because there are infinite. When you try to show something is a fraction, you just need to find out that fraction. For example, I want you to show 2 is a fraction. See, I can show you. See, this is fraction. Well, if I want you to show 0.333333 is a fraction, you can just show me it's one third. Okay, so it's easy to show something is a fraction. But I give you square root 2. I want you to show me this is not a fraction. Well, that's going to be hard because there are infinite many fractions. If you want to show square root 2 is not a fraction, you have to go through every single fraction we have and to prove that none of these fractions we have is equal to square root 2, which is impossible to do because there are infinite many fractions. All right. So usually whenever you want to prove something is irrational, you're not going to be able to prove it directly. So you are going to have to use indirect proof, or you call it proof by contradiction. Okay, so now we're going to follow, again, this is just my thinking, the formal proof here. Step 1. Okay, so you can say, well, I can change a different way of writing. I say it before, I didn't, in the previous example, I didn't write it down. So I just want to show you different ways. So previously I just said, suppose that something, or suppose to the contrary. So now I'm going to write a different way. So by way of contradiction. Okay, this is often abbreviated as BWOC. Okay, so sometimes you can just write on BWOC. Usually, most high level, if you read a research paper, usually when you see that BWOC, we know what it means by way of a contradiction. We assume, we suppose. We assume, okay, what do we assume here in this case? Following the steps.
Any irrational.
Mm-hmm. Wait, say it again. Say the whole negation, the whole thing. Negation of this. Mm-hmm.
An irrational number. Or any number is rational.
Yes. Okay. You were a little. You cut off a little bit. Let me see. But I think that's what you said. So assume what? The sum, you just copy the whole thing, change is to is not, or just change irrational to rational, right? So when we're going to assume the sum of any rational, oh, actually you shouldn't say any, right? The sum of a rational number and a irrational number is not irrational. If it's not irrational means it is rational. Okay. Right. So we want to prove for any cases, any rational plus any irrational, When you add them, you get irrational. But we're gonna assume, okay, what if you have this certain specific rational number plus another irrational number, we actually end up with rational. But again, we want to prove this is impossible. So this is our assumption, the first step. Go over that steps again. So you want to assume the negation is true. So that's the negation. So we learned how to write down negations before. Okay, so for any actually becomes there exists. So the other way to say it, you can say there exists a rational number and an irrational number such that the sum is rational. You can also say the other way. Okay, so here step 2 is to find a contradiction. Again, this is the important step, the difficult step. Where would the contradiction come from? So we're going to try to, again, start with the assumption to look what you can get from there. Okay, a rational number, I can write it as a over b. Irrational number, I can write it as x. So here maybe we can add a short sentence here. So let a over b, I'm sorry, let me just do it a quick way. A quick way will be just adding, okay, say a over b. Say x. Okay, so we're saying the sum of a rational number, say a over b, and a rational number, say x, is rational. And also here, a, b are both integers, where a, b are both integers, and b is not equal to 0. Okay, so now we get a conclusion. A over b plus x, because the sum is addition, is rational, right? Then this is rational. So notice what I just did was to change this English sentence to mathematical symbols. So I used A over B for the rational number, X for the irrational number. And after adding is rational. Well, if you know something is rational, you can describe it as a fraction. So since I already used A over B, I cannot use, maybe I just say or equivalently plus X equals C over D. Where does C over D come from? Because our assumption says the sum should be rational. Rational number can be described as a fraction. So I use C over D. Okay, where C, D are both integers and D is not a 0. Okay, now take a look at this expression. That's what we got from the assumption, our assumption. A over B plus X equals C over D. We still don't see a contradiction yet, but we're going to do one more step of algebraic work. You're going to be able to see what the contradiction is. So I'm going to solve for X. How do I solve for X in this equation? What can we do? How do we get X by itself?
Subtract A over B.
Yes, very good. Thank you. So you can subtract A over B from the left, subtract A over B from the right, from both sides. So A over B minus A over B, they cancel each other. So you end up with C over D minus A over B. Let me use a different colors. C over D minus A over B. Now that's algebra. You can equal a denominator to get a common denominator, which is BD. So multiply by B and B, and multiply by D and D. Subtract straight across BC minus AD. And look at this expression. What does this tell us? BC minus AD over BD? What kind of number is this when you see something, expression like this? Something over something?
Rational.
Yes, very good. Thanks. So rational. Now, what is rational? Don't forget, this is the same as X, right? So it says X is rational. Do you see what a contradiction is now? X is rational. What is X in our assumption? X is irrational, right? And we just proved X is rational. That is a contradiction. So when you look for contradiction, these are two things now kind of like against each other, right? So as a one number, it cannot be rational and irrational. Again, a number cannot be even and odd at the same time. A number cannot be rational and irrational at the same time. So here's the contradiction. So sometimes I don't know, you could use something like that to describe the arrow pointing against each other, towards each other. It's like saying, okay, they are against each other there. It's a contradiction. Okay, so here you can use sentence. It just says, contrary to the assumption that X is irrational, or the the condition. Or I can just put a contradiction here. When can we write down a contradiction? When you believe the contradiction is very obvious, everybody should be able to see it. So maybe as beginners, you should still write down clearly what contradiction is. So here I'm showing you different ways you could possibly see in the proof. So sometimes maybe a lot of times when you read a research paper, math paper published on any journal, a lot of times you just see a contradiction because the author assumed everybody can see what a contradiction is. So in this case, if you believe it's obvious to everybody, because I just proved X is rational, but I said at the beginning X is irrational, so that's a contradiction. So what does the contradiction tell us? It tells us, okay, this has to be false, which means that our assumption, whatever we assumed, this whole statement is false, which means the negation has to be true. So this must be true. All right, so you can add one more statement. So well, therefore, the sum of any rational number and irrational number is irrational. Okay, why? Because we just proved the sum cannot be rational, because if it is rational, we're going to end up with X being rational, which is impossible because X is we're going to end up with X being rational, X being rational, contrary to that X is irrational. So this assumption just tells us the sum cannot be rational. The sum must be irrational. Okay. All right, so this is a third example. Any question about this one? In the textbook, I think they have, let me see what else. That's pretty much, I think they have one more example that I didn't go over, but I think that should be, maybe I can also, okay, maybe I can also do another, there's another one in the textbook, another example that I didn't cover. Okay, let's see. There's another one which says, which I just mentioned, we used it as a fact, but we can still prove that. So I just said, when you have a integer, it cannot be both even and odd. We know it as a common sense, as a fact. But if you want to prove it, we can also prove it. So a lot of things you may assume that, like, there's no greatest integer. In algebra class, everyone knows that. We just assume automatically it's true. But in this class, we actually can formally prove it without just, oh, well, the teacher told me there's no greatest integer, or I just think, I just thought about it, there's no greatest integer. Or I just like this example 4, there is no integer that is both even and odd. No integer that is both even and odd. Because we just know this by thinking of some examples, like 3, it's odd, it's not even, and 4 is even, it's not odd. So we don't really see any. We picked a few numbers and we checked. We can't find anything that is both even and odd. So that's just, we say, okay, there's no integer. But technically, we didn't prove it. We just picked some numbers. How did you know? Maybe there is a very large integer that is both even and odd, or maybe there is a very small negative integer that is both even and odd. And so technically, we didn't really prove it. We just give some examples. Okay, so we actually can formally prove it. So first step, we prove by So the other way you can write is suppose not. This is the easy way to write it. Suppose not. Okay, so formally you could write down. I mean, this is also accepted when in proofs, unless in the published papers, because in this case it's very straightforward. So when you say suppose not, it just means the negation is true. But a lot of times we will write down the whole thing, the whole negation, so you can see clearly what you have in your assumption, especially when your assumption is very long, very complicated. So in this case, you can just put suppose not there, but you can also say, right, if you want to write down clearly, what do you assume? Suppose there is a integer, because they said there's no, right? So I'm going to do the negation. There is an integer that is both even and odd. That is both even and odd. Okay, so let's find the contradiction. Okay, so this integer, I don't know what it is, but since you said it's even, I can describe this integer as, so maybe since it is even, since it means, I guess I should be clear, since this integer is even, how do we can describe it algebraically, right? So let 2a be this integer, because we can describe any even integer in this format, 2a. So a is the integer here. Okay, well, it also says it's odd. Since this integer is also odd, I can describe it as 2k plus 1 or 2b plus 1. Let 2b plus 1 be this integer. So what I just did was to describe this integer in two different expressions, which are both okay, because if you tell me this integer is even, I can write it as 2a. If you tell me this integer is odd, I can write it as 2 times integer plus 1. Since they are the descriptions of the same integer, they must be equal to each other. So 2a must equal to 2b plus 1. Okay, this is because it's the same integer. So here, let's look for a contradiction. So how do we find a contradiction from here? Can you see a contradiction from here? If not, you can do some algebraic work. Just like previously, when I get here, when I get this equation, rational plus irrational equals rational. When I look at this, I still don't see what a contradiction is. But after I get x by itself, I did some work to this equation. I found out, oh, well, I realized x has to be rational, has to be a fraction. But x is irrational. Irrational cannot be a fraction. So that's how I got a contradiction. And similarly, when I did the second example, after I assume n is odd, I got n equal to 2k plus 1. But right now, I don't have any contradiction yet. But after I square it, I found out n is odd, which is contrary to n squared is even. So same thing here. When I look at this, okay, this integer can be described as even number and also an odd number. Well, we still don't see contradiction, but I can move 2b to the left. So I subtracted 2b from both sides. They cancel each other. So right hand side we're left with 1. The left hand side we have 2a minus 2b. And let's factor out. When you look at this, if you still don't see a contradiction, you can do one more step, factor 2 out. And that should give you a contradiction now. Can you tell what the contradiction is? On the left-hand side, it's a multiple of 2, right? On the right-hand side, it's 1. So this is like saying, what does this tell you? 2 can go into 1, which is impossible, right? 2 cannot go into 1. Or in other words, 1 is a multiple of 2, and that doesn't make sense, which means you can factor 2 out of 1. We know we cannot factor 2 out of 1. So that tells us a contradiction. So right here, or maybe you can even do one more step. What's the next step? If you say I still cannot see it, you can divide both sides by 2. So one more step like the textbook did. You can divide both sides by 2. So 2 cancels 2. So we end up with A minus B equals 1/2. Because this 2 cancels that 2, right? And look, what is A minus B? Because we know A is integer, B is an integer. A minus B has to be integer. So this is an integer. But look at the 1/2. 1/2 apparently it's not an integer. So how can an integer equals a non-integer? Okay, so I guess I mean, either way, you could stop right there, just say 1 cannot be a multiple of 2, or you can say an integer equals 1/2. That's impossible. Okay, so here is a contradiction. And once you found a contradiction, you can stop there. So, and there is no, just copy the statement one more time here. So there is no integer that is both even and odd. Okay, well, the whole process can be simply summarized as this. If there is an integer that is both even and odd, you're going to end up with a contradiction. What's the contradiction? A minus B will be a fraction. An integer will be a fraction, which, maybe I should say it's 1/2 cannot be an integer. In other words, 1/2 cannot be an integer. So that's a contradiction. Okay, so if there is an integer that's both even and odd, you're going to end up with 1/2 being an integer, which is impossible. So that tells us you cannot have any integer that is both even and odd. Okay. All right. Questions? So that's all the examples we have in 3.6. Really, I think to understand how to write indirect proofs, you're gonna have to do practice. So the homework assignments will give you some practice, and you can follow the examples I did today in class and try to see if you can do it. Again, if you have trouble, email me and let me know. So you can, at least you should be able to write down the first step. Suppose not, or suppose the negation is true. And then try to, work something out. If you get stuck somewhere and you say, I can't find the contradiction, you can take a picture and email to me, and I can point you to the right direction. Okay, we have a little bit of time, 10 minutes. So I can maybe cover one more example in 3.7, 2 classical theorems in number theory. And this is also indirect proof. So it's the same type of question, but we put it in a different section because these 2 theorems are 2 classical theorems in number theory, and also they are a little harder than the previous examples we did in 3.6. So in 3.6, most of the time, the contradiction doesn't take very long for you to find. Well, maybe this one actually maybe takes you a little bit of time to realize what the contradiction is, but most of them it's just one step. So you get X by itself, you see what contradiction is, and you square. I mean, I did do step-by-step algebraic work, but really when you get this, you can, if you skip all that algebraic work, and you can see what n squared is odd immediately. Okay, so most of the examples in 3.6, and the first one is even easier, so you can see the contradiction immediately after you add 1. But in 3.7, and then that's actually the case most of the time in high-level math or in number theory, a lot of times the contradiction is not very easy to see. Okay, so prove the square root of 2 is irrational. If you took a math history class, we did do this in that class. So you want to prove square root 2 is not a fraction. In other words, cannot be equal to a fraction. That's why we need to prove. Again, like I mentioned before, it's very hard to prove square root 2 is not a fraction, because if you want to say, you have to list all the fractions you have and verify that none of these fractions is equal to that. I mean, I guess technically I should use bigger numbers like that. So you're going to have to verify all the fractions you have, even many of them. None of these fractions is equal to square root 2, which is around possible approximately 1.414 ... and forever. Okay, so that's not an approach we can do because we don't have unlimited time to verify unlimited fractions. Unlimited number of fractions are not equal to square root 2. So that's not a way to do the proof. So we can use indirect proof again. So suppose not, or suppose, as we did before, it's hard to prove something is irrational, but we're going to assume square root 2 is rational. See what happens. Again, if you know anything is rational, you can assume it's a fraction, a over b. So we actually want to prove square root 2 is not a fraction, but I'm going to assume it is a fraction. Just like in real life, you want to prove you're innocent, but you assume you are not innocent. And then find a contradiction which proves that you are innocent. Okay, so I'm going to assume a over b. Square root 2 is a fraction, a over b. A, b are both integers. B is not equal to 0. And there's one more assumption, which is very important. Because fractions, you could have a non-simplified, non-reduced fraction. Let's say 4 over 6. That is also a fraction. But after you reduce it, you're just going to get 2 over 3, right? So A and B, which one did you take? Is that a 4 over 6 or 2 over 3? So we are going to make sure we always take the reduced form. So which means the greatest common factor or divisor of A over B is equal to 1. Okay, so this means usually you can just use GCD, greatest. I'm going to put it in words here for you. Greatest common divisor, or you can call it factor in algebra. Divisor of A and B is 1. In other words, 1 can go into both of them. For example, 2 of 3, 1 can go into both of them, but you cannot find any number that except 1 that can go into both because you're going to reduce all the common divisors. Okay, so why is this very important? How did I know I should pick a reduced fraction? Well, because whoever came up with this idea of proof already, well, whoever first came up with this proof is, I guess, very, I don't know what's the right word to describe that, very smart. And then they just told us, okay, this is the thing you're going to use. And that will give you, this assumption with condition will give you a contradiction. Okay, there are actually other ways to prove it, but this is just one of the common method we use in number theory. Okay, so now, so remember, this is the one you're going to find a contradiction with. Suppose, so now let's see, how do we find a contradiction then? So this is the difficult part right here. It doesn't just take one step. Where do I start with? This is the only thing I have, only description, only equation I have. So I'm going to look at this, see if I can get any contradiction from here. And again, when you look at it, well, square root 2 is a fraction. It's possible. Well, although we know as a fact it's not possible. But right now we're doing indirect proof, so it's just possible. So right now we don't see any contradiction yet. But we can square both sides to get rid of a square root because square root is usually hard to deal with. And after square both sides, square of square root equals 2. Square of A over B is A squared over B squared. Now we get fractions. We're going to next get rid of fractions, again, because fractions are not very easy to discuss either. So I multiply both sides by B squared. So I can cancel B squared on the bottom to get B squared on the right-hand side and 2B squared on the left-hand side. All right, so take a look at this expression. What does this, look at this equation. 2 times B squared equals A squared. What conclusion can you get from here? Can you get any conclusion by looking at this equation? I may give you a hint. 2 times the integer. Remember, b is an integer, right? If b is an integer, b squared has to be integer. So this left-hand side is exactly the format of 2 times the integer. So does that sound familiar? 2 times the integer. What does it remind you? When you have 2 times the integer, what does it tell us?
It's even.
Yes, that's right. Very good. So what is even, to be specific? So this is 2 times the integer, right? Which means that's the left-hand side. Left-hand side is even. Well, if the left-hand side is even, what about the right-hand side? So this is even. What about right-hand side? Also has to be even, right? Why? Because they're equal. It's just 2 different ways of writing it. So sometimes when you have a number, you can, for example, you could write 2 plus 2 equals, well, maybe change it to a different one. 2 plus 4 is 6. Or 2 times 3. So you could have 2 different ways of writing the same number, right? So the same idea here. You could have the same number, which can be written as a squared or 2b squared. They're both even, right? Okay, so if you know 2b squared is even, that tells you a squared is also even because they're the same, they're equal. Okay, well, so from here we can get a conclusion. So a squared is even. And if you think you need a more explanation for that, you can, I mean, I think it should be straightforward because 2 times integer, right? So a squared is even. Okay, if you remember at the beginning of the class, the first example I did, what conclusion can we get from here? Let's go back to this, I'm sorry, the second example we did. If n squared is even, then n is even. Maybe let me write it down here, up here. So that one of the statements we proved, if n squared is even, then n is even. You can apply the theorem we just proved. Here, what can you say about a? So we know a squared is even. By this theorem we proved, what can we say about a?
It's also even.
Yes, right? Can anybody see that? It's just pretty much says if you have a square of a number is even, then the base has to be even. So it's just different variable, n and a. Very good. So a is even. All right, if a is even, right now I still don't see any contradiction. So okay, a is even. It's possible for a fraction to have an even numerator, right? So let's continue. So let's assume a equal to 2k. Because whenever you know an even number, you can immediately assume it's a 2k. And you're going to plug back into the equation that you just got. We just got 2b squared on the left-hand side. But we're going to replace this a with 2k because we know more detail about a now. And simplify the right-hand side. Well, after I replace a with 2k, I got 4k squared. And keep simplifying this further. Divide both sides by 2. So we want to simplify it as much as possible until we can see a contradiction. Now let's focus on the simplified equation. B squared equals 2k squared. What conclusion can you get? Similar to this one. What conclusion can you get from here? B squared equals 2 times the integer. See, this is 2 times integer. So what can we say about it? B squared?
It's even.
Yes, Molly, thanks. B squared is even, right? Because b squared is 2 times the integer, which means 2 goes into b squared. So b squared has to be even. Well, if b squared is even, again, apply the theorem we proved before. If the square is even, the base has to be even. So in this case, the base is b. So b is even. Okay, right now, I want you to take a look at these 2 statements we proved. A is even and b is even. If the a, b are both even numbers, what do they have in common? They must have something in common. Even numbers all have what in common?
They can be divided by 2?
Yes, or they have a common divisor 2, right? In other words, yes. So A and B have a common factor, or you can call it common divisor, a common divisor or factor 2. But did you see what a contradiction is now? Look at the assumption that I mentioned at the beginning. What did we assume A and B? What's the greatest divisor they have? 1, which means you shouldn't have a common divisor 2. Nothing, because when I picked this fraction, I made sure this is a reduced fraction. But now we found out they should have a 2. So it's like 4 over 6. They both have a 2 in common. You can continue to reduce 2, right? So that's the contradiction. When I picked that at very beginning, I didn't pick 4 over 6. I picked 2 over 3. But I ended up with still A and B have 2 in common, which is impossible. So that's a contradiction. So you can say contrary to the fact, the assumption, contrary to A over B is equal to 1. So this contradiction tells us, well, this has to be false, cannot be rational. Where does the contradiction come from? It comes from that assumption that assumes square root 2 is rational. So that means it cannot be rational, which means irrational. Okay. So square root 2 is irrational. All right. Okay, this one is much harder than the one we did before. So next Tuesday, I'll give you another example. And so for today's homework, you don't have to worry about the examples like this. So as long as you can do like a simple one, like probably most of them just gonna be like 1 step, 2 steps at most to find a contradiction. Okay, let's stop here for today. So again, don't forget to take the exam and have a good weekend. See you next Tuesday.